Hey everyone, welcome. Today we are talking cosmology, inflationary cosmology, Big Bang, microwave background radiation, all that wonderful stuff. And the person that we're speaking to is one of the people who has been one of the prime architects of our current understanding of cosmology, someone I've known for decades. So I'm so pleased to welcome David Spergel to the program. He's currently the president of the Simons Foundation. Prior to that, he was a chair professor of astronomy at Princeton University, where, among other accomplishments that we will discuss today, he played a pivotal role in WMAP, the Wilkinson Microwave Anisotropy Probe, which mapped the cosmic microwave background radiation with unprecedented precision at that time. And in 2018, he was named winner of the Breakthrough Prize in Fundamental Physics. Welcome, David, and I believe you're joining us from your office at the Simons Foundation. Is that correct? Is that where you are now?
That's where I am.
Yep. Fantastic. And when did you move to Simons from Princeton?
So I first moved here almost 9 years ago.
Oh, that long.
And I moved to initially a part-time position. So Jim Simons asked me to set up the Center for Computational Astrophysics at the Flatiron Institute. Yeah. And I split my time between Princeton and New York doing that, then moved to New York full-time about 6 years ago, 5.5 years ago. And then became president of the foundation just over 3 years ago.
So that's quite a change from being at the blackboard to managing a major foundation of that sort. How's it been going? Is it a change that you've enjoyed?
I've been enjoying it. I think it was a transition from being a specialist to being a generalist. You know, in discussions of cosmology, I kind of knew my stuff.
Right.
And now when I walk into a room, whether it's hearing what we're doing in neuroscience or mathematics or talking to our investment team or HR, I'm usually the person in the room who knows the least. And the way management works, that means I'm the one who makes the final decision.
Yeah, right. But also, I imagine a wonderful opportunity to just get an overview of science as a whole that's difficult to get in any other position.
I feel like I'm a college freshman again. I'm so constantly learning, constantly trying to pick stuff up.
And speaking of college freshmen, or perhaps even earlier, I can't help but notice a particular book that I think is above your left shoulder, if I understand how the mirror symmetry here works. Meisner, Thorne, and Wheeler's book on gravitation, the big black book over there on your shelf. That, to me, was one of the amazing learning experiences when I went through that book. Did it also play for you a similar?
A huge role. Yeah. So when I was a sophomore at Princeton, I took a course on general relativity that Rich Gott taught. And we used, this book has 2 tracks. Track 1, which was meant for kind of an introductory undergraduate level book, and track 2. And I took the book, and Princeton had a schedule at the time where classes ended, I don't know, December 15th. Then you went home and you took your finals at the end of January. So you had like 6 weeks to prepare for finals. So I took the book home and I read track 1. And I thought this was so cool. And I decided to work over those 5 weeks. I spent my time, sometimes being at home. My now late parents wasn't the most exciting place to be. And I just taught myself general relativity from that book. And I thought it was so exciting that that's what I decided I want to focus on, was general relativity and cosmology for graduate school.
Yeah, I had a similar experience both with Meisner, Thorne, and Wheeler, also with Weinberg's book. In fact, early on when I used to give technical lectures to a variety of audiences, I often had a track 1 and track 2 in the lecture itself, inspired by the book, for the specialists and for the generalists. So yes, a vital step. So I also recall and was reminded, you and I ran into each other at dinner just a couple nights ago at the Math for America Gala here in New York City. We were both a bit stunned, I think, to realize that we'd known each other for about 40 years.
That's right.
Meeting back in Oxford. And I also realized we have a lot of influences in common. So Bill Press was my undergraduate advisor. I think was your graduate advisor. James Binney was my first graduate advisor at Oxford. And I think you wrote early papers with him as well, right?
Yes. Yeah, so James was my advisor as a junior at college. He was a visiting professor at Oxford, from Oxford coming to Princeton.
Right.
Yeah, so I worked with him on galactic dynamics. My girlfriend's senior year got a Rhodes Scholarship. I wrote to James to follow her to Oxford. By the time I got there, that relationship was over, but I had a really productive year studying with James at Oxford for the year.
And that's where we overlapped the first time, I think.
And we overlapped for the first time there.
Absolutely. And we wrote even a paper, I think, on dark matter or something of that sort of like.
So what I remember from that paper is we wrote a paper on dark matter where we looked at a more general supersymmetry model.
Right.
And we were doing this illegally, in the sense that it was neither my thesis nor your thesis.
Right.
And we didn't tell our advisors. And we got a negative referee report, but one we could have responded to.
Right.
And we were so young and naive that we didn't respond. We didn't tell our advisors. And that paper's unpublished.
That's right. So we can revisit it, that means.
Well, we could, though I think the idea in the paper, which was kind of ended up being the lightest supersymmetric particle, being a more general form of Higgsino and Photino. Right. About 10 years later, the world caught up to us, and I saw that paper published. So I don't think we can publish it yet again, but who knows?
There you go. 10 years ahead of the curve. So then, of course, you went on to be a professor at Princeton, and I want to turn to, I mean, you've done so many things, but I want to focus on WMAP if we can for a little bit. So WMAP, of course, was this critical experiment giving us insight into the microwave background radiation. Maybe, I think most in our audience are familiar with it, but just give us a quick background on the background radiation first.
Sure. Let me actually give a 30-second detour.
Sure.
Because just how I got into WMAP.
Totally.
Because I spent a lot of my first few years at Princeton looking at an idea for how structure formed called phase transitions in the early universe. And when the COBE results came out, I realized I had spent 4 or 5 years pursuing something that was just not the direction the universe chose.
Mm. And you were looking at like cosmic strings and things?
Cosmic strings and textures. Okay. And superconducting cosmic strings and all that stuff. And I organized a conference after the COBE results that came out about what it meant. And at that conference, I met Chuck Bennett, who would lead the WMAP experiment. And he would eventually invite me to join WMAP. So it was one of these moments where things failing actually led to my getting involved with what I think of as the most important thing I did scientifically in my career.
Yeah.
It's just failures often lead to the next.
No, it's an important message, especially for the young people in the audience, to know that you just can't plot out a career in any arena, but certainly in science, there's serendipity and things that you wouldn't have expected that lead to one or another path that you happen to choose. Now, WMAP as a machine, it's a device, it's a thing that actually measures the properties of the temperature in space left over from the Big Bang. As a theorist, what role do you play in that? Do you do calculations that help the people who are actually building the machine know their design specifications and so on?
So I think the answer is yes. So we, made simulations of what we thought it could measure. We realized, and this is how I got involved, that if we were able to make very accurate measurements of the microwave background, we could determine the basic properties of the universe. Or really what we said at the time was, there are two possibilities. Our current model is wrong, and as our data improves, that's what we see. Or the model's right, in which case we can determine the basic parameters like the age of the universe, how many atoms there are, how much matter there is, how lumpy the universe is, and how that lumpiness varies with scale from the measurements. And as we went to simulate what it would be like to make those measurements, we realized that we would gain a lot by being able to measure polarization, so that the theoretical work helped push the experimentalists to develop that capability. And we realized we had to measure things like what we call the beam, how the camera responds to a signal, right? And I think it's something that people have seen with a telescope. When you look at a star, you'll see X's that come off the star. And that's part of the response of the telescope to the image. And we realized to get really accurate measurements, we would have to make accurate beam characterizations. So one of the things we did in the project before it launched was work with the experimentalists to determine what are the requirements on what we need to measure really well, but also what things we're less sensitive to and how we might calibrate it. So it was a really interesting experience to be part of that.
And that was a relatively small group early on, right? I mean, some of these are enormous collaborations where everybody has
yeah. So there were like 8 of us who were the lead people on it. There were about 30 people on the team, including a lot of the graduate students and postdocs and some of the engineers and research scientists at Goddard Space Flight Center. So we were a small team, and within that, like for each piece, there was only a handful of us working on the analysis, a handful of people designing the detectors. It was actually great because we all knew each other. We communicated really well. There were too few of us for the project, which meant we all had to work really hard. And all of our time and energy went into doing the science. And sometimes on these big collaborations with hundreds of people, a lot of time and energy goes into politics. Yeah. And this was all just working hard and understanding and learning things. So it was a terrific team to work with.
And Gary Hinshaw, of course, was one of the lead people on this as well. He was my teaching fellow when I was an undergraduate at Harvard, taking so many. I had him for so many classes. The nicest teaching assistant that you ever had. So I can imagine that certainly would have helped this working arrangement.
Gary was a real pleasure to work with. I actually also first met Gary at Harvard. So when you were an undergrad, I was a graduate student. And Gary and I were actually in a lot of classes together at Harvard. And had exchange.
And so all that work was happening. This is in the 90s. And then WMAP launched when? Around 2000 or so.
2000, yeah. So we started the project around 94. We started talking to each other about it. I think our preliminary study got approved in 95 and the proposal in 96. So for a space mission, it actually went really
incredibly
quickly.
Fast, right?
Yeah. So, it was a design for the Explorer program, and you had to have the technology ready to go. And in many ways, we built on COBE, which was the first mission to see the microwave background fluctuations. And we built on it in COBE in a bunch of ways. Lessons learned in terms of how you design an experiment like that. But probably most importantly, the science team.
Yeah.
Chuck Bennett, who led it, had played a key role in COBE and kind of learned a lot on how you get a mission done and get it done quickly and effectively. And I think that was a big factor in its success. I mean, it was a impactful mission that got done quickly and at a relatively modest cost.
And so you mentioned quickly the science background. So you've got the hot Big Bang, heat left over, 380,000 years after the Big Bang, atoms and the nuclei, electrons come together, they become neutral, releasing this radiation to travel through space. So you can measure its temperature variations, but you mentioned word polarization as a key part of what was and going forward will be the impact. Just give us a sense of where polarization comes into the story.
So I think of it this way. When I look out in space, I look back in time. And, near stars, a few light years away, you look back a few years. Microwave background, you're looking back 13.8 billion years. You're looking back to when the temperature of the universe was about 3,000 degrees and was ionized. And you're seeing light that last scattered off electrons. And the key word is scattering. So if you're looking at, you go to the beach, you look at the sky, you see scattered light that's polarized, because it's either scattered off the ocean surface or scattered off of molecules in the atmosphere. And that scattered light has a polarization. And that's why you put on polarized sunglasses, because it blocks, there's two polarizations you can think of: the photons coming to you with their electric field pointing this way, or maybe pointing that way. And unpolarized light has equal amounts this way and this way. Polarized light might have more this way. And if you've scattered off a surface, you'll have more light polarized that way. So that we're getting information both by measuring the intensity of light and by measuring its polarization and the polarization pattern.
Yeah. And so soon after WMAP launches, you begin to get data. And I think we actually even have a graphic that compares the sensitivity of, say, even Penzias and Wilson, then to COBE, and then to WMAP. Obviously, you were quite pleased with the data as it came in. So what was that like, and what did you find?
It was really exciting. Here's our map of the microwave sky. You can see this pattern of hot spots in red, cold spots in blue. These variations in temperature are tiny. They're a few millionths of a degree, maybe a variation of 100 millionths of a degree from the hottest spot to the coldest spot in these maps. And you can see spots with a characteristic size and an amplitude that depends on scale. And by measuring those properties, we can learn a lot about the fluctuations. We can learn, for example, you can do things where you reverse the hot and cold colors and ask if it's symmetric. So you can learn about the properties of the initial fluctuations. I think the lesson we learned from this is our universe was remarkably simple. We could take this complex pattern and characterize the fluctuations completely with sort of 6 basic numbers when we look at all the observations, including the polarization. How old the universe is, which we measured with an accuracy of better than 1%. How many atoms there were in the universe, what's the density of atoms relative to photons, which we also measured with accuracy of better than 1%. We directly saw in the microwave background the gravitational effects of dark matter, and that the dark matter behaved differently from atoms. It didn't move. It wasn't coupled to the photons. And so we measured the density of dark matter. We measured how lumpy the universe is, how that lumpiness varied with scale. And we also were able to detect the signature of the formation of the first stars that ionized the universe and produce some additional polarized signal. So those characterize everything we see in the microwave.
And just to understand how you get to that conclusion, presumably we have theoretical models that you can simulate on powerful computers, and there's some parameters, the ones that you just mentioned. And you're saying that if you change those parameters by even a small amount from the values that are preferred to match the data, they just no longer match the data.
So you can match those parameters, fit them to this data. Then once you fit them, you've got the basic parameters of the universe. So you can basically predict what happens afterwards. So you can predict from these observations, what should the large-scale distribution of galaxies look like? And then turn to surveys like the Sloan Digital Sky Survey, or now the Dark Energy Survey, and ask, does what we see in the early universe match what we see today?
Right.
You can compare it to measurements of the expansion rate of the universe, measurements of the age of stars. So if we say the universe is 13.8 billion years old, there better not be 15 billion or 20 billion year old stars. And What I still find really surprising is this simple model fits at least all the data we have at the moment. And it's, when I think about scientific models, you can ask, like, will they stand the test of time?
Yeah.
And I think of this in terms of the solar system. Newton's laws, Kepler's equations, of, all the stuff developed 500 years ago, at the level of explaining the motion of the planets, Newton's laws hold up today. We know general relativity is a refinement of it and affects some of the details, but the basic picture that we had 500 years ago was right. And with any model we have, like our current understanding of the microwave background, it could turn out that I think it's a reasonable chance that we've got the basic picture right, that our estimates of things like the density of atoms or the age of the universe will hold up in 50 years or 100 years. I'm certain there'll be lots of things we don't understand now that we will hopefully understand better then. But I think we have, with our microwave background observations, established a cosmological model whose basic pictures has stood the test of the last 20 years and maybe will stand the test of the next 100.
Now WMAP, early 2000s, then there have been a lot of future relative to that moment in time experiments, notably the Planck satellite. Mm-hmm. Have you found any tension between the newer results and the older results, or is it simply refining and getting things even more confident?
If we look at the microwave background observations, they're remarkably consistent. If you look at a picture of what WMAP measured and what Planck measured, smooth. So Planck has higher resolution. It sees lots of details that weren't seen in WMAP, but at the level of the same resolution, the pictures look identical. If I showed you the two, you'd have a really hard time telling them apart. And so you can see Planck sees details that WMAP doesn't, but you smooth the Planck data to WMAP scale and you get the same picture. You look at the parameters, Planck has measured them with more certainty. But WMAP, its numbers are very consistent with Planck. And we have lots of measurements from the ground, not of the whole sky, but of patches of the sky at higher resolution than Planck. Measurements from the Atacama Cosmology Telescope that I've been part of, measurements from the South Pole Telescope, a number of other experiments over the last 20 years. And all of those are also consistent with WMAP and Planck.
Yep.
And we see a very consistent story. Now, that's a consistent story looking at the microwave background. What has been interesting and exciting is to take those observations and compare them to the universe today. And most of the pieces fit. The one that has had some tension is the measurement of the Hubble constant, the expansion rate of the universe. We look at our microwave background observations from WMAP and Planck and the other experiments. We all get values consistent with it being about 68. When Adam Rees and his colleagues use Cepheids, which are a type of star that we can relate its brightness to how its period oscillates, the Cepheid brightness lets us calibrate them, and we can determine the distance that way. And they get a value of 72. And you think 68 and 72 are pretty close. But because these teams have worked so hard on getting accurately calibrated things, the error bars are small enough that there's a real tension between those values. Adam's team would say it's 5 sigma off. Now, people argue about error bars and so on.
But that's a big, but with the level of precision that we can now do, that's a real problem. You have to take it seriously.
So this has been taken really seriously, and it's telling us one or two things. Either there's some really important physics we're missing, right? And it's pointing to something that we don't understand about dark energy, about the expansion history of the universe, about the breakdown of general relativity, And there's a lot of papers that people have written over the last decade or so that have posed all kinds of new ideas on what might be going on and suggesting that this could be an insight into like something really important we're missing. And I think this is actually an important kind of history of science thing. Why do we care about measuring things accurately? Because when they don't fit and the numbers aren't consistent, it's something that can often point to a hole in our understanding, that there's something wrong with our models. So that's the exciting possibility. The second possibility is there's something awry in one of the measurements. Now, the microwave background measurements have been done independently using multiple experimental techniques. They're confirmed by large-scale structure measurements. So I think that measurement of 68 is pretty robust. The value of 72 relies on these Cepheids. And you'd like there to be other techniques and more precise measurements. And Wendy Friedman and her collaborators took a big step forward a few months ago, where they reported some results using the James Webb Space Telescope. And the previous values rested on Hubble. And James Webb is really a huge advance in capability beyond Hubble. And they've used 3 techniques. When they use the Cepheid technique, they get the same value as Adam. They get a value of very close to 72 or 73. When they use these 2 other techniques, also based on stars as distance calibrators, they get values very consistent with 68. So it could be telling us maybe there's something wrong with these other techniques. But most likely what it's pointing to, and I think this is interpretation at least I'd favor, is that they're telling us there's some subtlety. There's something we're not doing right in treating the analysis of Cepheids. And it's in both Wendy and Adam's analysis. My guess, and I'm not really an expert on Cepheids, but it has led us astray so many times in the past, is that it's dust, and that there's some subtle property of dust that we're not properly modeling that's systematically biasing the values.
Right. And has Adam weighed in lately? I mean, we've had a few conversations with him over the years on this, but I haven't spoken to him lately. Do you know if he's coming to that perspective as well?
I think when I've talked to Adam, he's still pretty convinced of his value. He has really spent a lot of the last decade refining the way that his measurements have done and have really carefully calibrated all pieces of the distance ladder. He and his team are also using the James Webb Space Telescope to do their own analyses. James Webb lets you observe the infrared, where the stellar properties are less affected by dust. And this is a situation where I think in 2 or 3 years, we will understand things much better. We'll have much more data from James Webb and be much more confident either that we have a very consistent cosmology or that there's a real problem with it. And that this is one of the big hints we have pointing out where there might be new physics.
So it's kind of a win-win. People may not fully appreciate that. No matter what happens, if it confirms the 68 kilometers per second per megaparsec that comes from early universe studies, that will be an amazing thing, that there's a confluence of all these results leading to one particular answer. And if it doesn't, it will open up the possibility, as you mentioned, that maybe there's new physics, new ideas that need to be brought into the story. So
this is one of the things that's made cosmology so exciting. It's like, because the instruments keep getting better, we're able to measure all these things more and more precisely. And we know more today than we did 20 years ago.
Yeah.
And some of the theoretical problems, which are deep ones, remain, but they've actually been, in many ways, clarified. Like, I think we now have really convincing evidence that there must be dark energy there.
Now, the theoretical context, if we can just slightly shift a bit, not moving far away from where we've been in this conversation, but the theoretical context within which all of these observations are generally understood is inflationary cosmology, the dominant cosmological paradigm, really for the past, 40 years or something of that sort. And so I want to just spend a few minutes talking about inflation because it's one of the interesting sociological stories in science where one of the founders of the inflationary theory, your colleague at Princeton, Paul Steinhardt, has had a dramatic change of heart regarding the inflationary paradigm, has introduced a completely different approach involving cyclic cosmology. But one thing in particular that I wasn't fully aware of until I was speaking to him a few months ago, and again, I don't follow this in fantastic detail, so I may not be fully up on the at the moment thinking on this, but he and Anna Iyas were doing these simulations of inflation. And one of the claims to fame of inflation is that it naturally gives a universe that is very nearly spatially flat. And it gives a universe that has all the properties that, at least in qualitative and quantitative detail, we would expect. But Paul's analyses using these simulations seem to suggest that the conclusions that were drawn regarding inflation were based on approximations. And when you do detailed numerical simulations, some of those properties of inflation don't seem to hold through, that you don't necessarily smooth out initial fluctuations and things of that sort. Has any of that caught your attention or changed your thinking about inflation?
So I think that inflation has a number of successes, right? It predicts, it was designed to explain the uniformity of the universe, the fact that the universe looks the same in that direction as that direction. And when the model was developed, it predicted there would be a pattern of fluctuations that looks remarkably like what we saw in the WMAP data. Fluctuations that are what we call Gaussian. They've got kind of this bell curve distribution and amplitude. Fluctuations that were invariant in scale, and fluctuations that existed on scales that, without something like inflation, would require that you imprint these in the initial conditions, or as Paul would and his colleagues would prefer, that the universe would go through a bouncing phase and that they were generated earlier. So the microwave observations already require either something happened early, whether it was inflation or something like that. The inflationary model's successes are all based on what happens towards the end of inflation. The fluctuations we see represent things generated in the last 60 expansion times, in what could be thousands of expansion times in inflation. The problems with inflation tend all to happen at the beginning of inflation. Inflation, in order for it to start, requires a patch of the universe be very homogeneous, very smooth, very uniform. So it's hard to say it answers the question of why is it so uniform when you have to start with a reasonably smooth patch. And you have to have the field have just the right properties. And many of Paul's criticisms, and I think they're very important ones, tend to point to problems with starting inflation. And how does it begin, and what were the initial conditions for inflation? What's the causal structure of the model there? There are other problems associated with what's called eternal inflation. The idea that most of the universe, volume of the universe, depends how you measure volume, is actually still expanding incredibly rapidly. And we're living in this small patch. Small patch could be 100 billion light years across, that where inflation has ended and we have special conditions. And this, as we start to address these questions, and this is in a sense your problem, because theoretical physicists have not yet solved the problem of how we unify quantum mechanics and general relativity, that we don't understand the initial conditions of the universe. And we don't understand how to embed the theories. The exciting thing is that solving those fundamental problems in quantum mechanics and general relativity, and and string theory is I think has been our best approach to this, our most accurately studied one so far, has the potential of answering those questions. So cosmology becomes the laboratory for addressing them.
So let me ask you. So the traditional canonical way of thinking about inflation, basically as put forward by Guth and Linde and Steinhardt and Albrecht in the old days, is you have some scalar field that fills space. In some patch, as you mentioned, it acquires a uniform value. When it has that uniform value, you can see right from the math, it yields a repulsive version of gravity that pushes everything apart, so on and so forth. Would you view that more as, in our language, an effective field theory description, just sort of a way of instantiating this idea of rapid accelerated expansion, as opposed to that is the way in which inflation is necessarily realized? Is that sort of a better framework for thinking about what inflation is?
I think of it as one of two things, kind of in terms of historical science, the history of either an effective field theory, and I think of, we're used to effective descriptions. Most of us, most of the time, think of the air around me as a gas. That's an effective description of billions and billions of oxygen and nitrogen molecules moving around rapidly. So there's something deeper going on as you go from gas to molecules. And maybe this effective theory is a field theory description of something deeper going on that may require an understanding of something like string theory. So that's possibility one. The second possibility, I look at the history of quantum mechanics. And there was what we called old quantum mechanics, which was developed by Bohr and had a few of the ideas of modern quantum mechanics, got the hydrogen atom right, but couldn't predict other things and had a lot of contradiction in it that led eventually to Heisenberg and Schrodinger and Einstein and others developing modern quantum mechanics. So it could be, inflation could be a step on the way to the ultimate theory, or it could be an effective theory. I think we don't know yet. It lets us do real calculations, which is useful. It predicts things like the presence of gravitational waves that would have been generated during inflation. And these are gravitational waves on scales much larger than what we look at when we look at the waves produced from merging black holes. And so the next step in microwave background research, and this is something that we're funding actually at Simons Foundation through Simons Observatory, is looking for the signatures that these gravitational waves make in the pattern of polarization of the microwave sky.
And so I think we have an image of the Simons Observatory. I'd love to bring it up, and just if you could tell us a little bit about that. And I would love to delve into the physics of gravitational waves from the early universe impacting the microwave background, as that's a vital part of the next story, as you just described. So what are we seeing here?
So you're seeing one of what we call the small aperture telescopes. This is a telescope designed to measure the pattern of polarization on large angles of the sky, scales of a degree and bigger. So we're making a kind of a rough map of the sky, but with enormous sensitivity. And you can see that we're on a mountaintop in Chile. This is, 14,000 feet above sea level, a place that's really high, really dry. You can see a nice dry sky up there. So it's a terrific place to make these kinds of observations. And what we want to do is look at the polarization pattern. And if we were looking at only variations in density and temperature, the things that we saw in that microwave background picture you saw, the polarization pattern would be what we call an E-mode pattern, something that's symmetric in a mirror, or also something where you can think of it as it looks kind of like that, just up and down. There's no net sense of rotation with it. Gravitational waves generate not only E-mode fluctuations, but what we call B-mode fluctuations, fluctuations with a net sense of rotation. And if we can see these B-mode fluctuations and show they're cosmological, that they're in the microwave background, this would be the way we could detect cosmological gravitational waves. One of the signals predicted by the inflationary model, something generated during the first 10 to the minus 30 seconds of the Big Bang. And this is actually a way we could observationally distinguish between the inflationary idea, which predicts the existence of gravitational waves, though it doesn't predict its amplitude, so we don't know what the signal's amplitude should be, and Paul Steinhardt's model with a bouncing cosmology that does not predict gravitational waves.
And so this idea of detecting gravitational waves from the Big Bang through their influence on the microwave background radiation is absolutely vital. And it may bring to mind those of our audience who follow science news really closely. There was a time in the not too distant past where there was a claim that such an impact on the microwave background radiation had been found, right? And that turned out to not actually be correct. So
yeah, so there's an experiment in the South called the BICEP experiment, and it was mapping these polarization fluctuations, and it saw them, and it had the right pattern and amplitude that it was plausibly the signal. But they observed this primarily at one frequency, and they didn't really have the data to distinguish whether I think of this as I'm driving my car and I see this interesting pattern, and am I seeing something profound in the distance, or am I seeing dirt on my window? And what they were seeing was effectively dirt on the window.
Right.
Not dust in their experiment, but dust in our own galaxy. That was, dust particles that were a few thousand light years away, not tens of billions of light years away, like the microwave background. And it was a signal in dust. The team unfortunately jumped to the most exciting conclusion first. I was one of the people who pointed out that this was likely dust. We did a reanalysis of their data, and that was confirmed. For me, this is actually an important lesson in how science works. People try to make important claims. If the important claims have profound effect on science, detection of gravitational waves will be a really important discovery. Other people test it. And we reanalyzed their data, as did a few others. We reached a different conclusion. And the Planck team took their data, which was coming out about the same time, and they reanalyzed it and reached the conclusion it was dust. And subsequent measurements have all been consistent with dust. And the team of scientists that made this measurement effectively withdrew their claim and now recognize it was just dust.
No, it's important because it shows how science has this wonderful self-correcting capacity to perhaps go on a bit of a random walk toward truth, but ultimately we settle upon things that the community can agree upon. So it's absolutely essential. But one point that you made a moment ago is that we, from the theoretical ideas, don't know the amplitude of the gravitational waves. Therefore, we don't know the strength of the signal in the polarization of the microwave background radiation. So failure to see the B mode polarization would not rule out the inflationary paradigm. And so it naturally raises the question, is the inflationary theory itself a falsifiable framework or not? It's a subtle and difficult question to address, but where do you come down on that? Is it more of a package deal that allows you to explain the current data really well in a very clean and simple framework, or is it truly a falsifiable framework for cosmology?
I think it's falsifiable in two different ways. Theories fail because they're actually not mathematically consistent, as it were. And we do not have a theory of inflation that fully incorporates the initial conditions and takes the universe from its first moments of the initial singularity all the way forward. So it could be let's be optimistic. And 20 years from now, we have ideas that come out of string theory or some of its derivatives or alternatives that looks like a complete quantum gravity theory that predicts the standard model of physics, predicts some new physics that you can verify experimentally, and is all elegant and consistent. It's the new synthesis that replaces what we have the way general relativity replaced classical physics. And that consistent theory, which had all these other successes, was not consistent with inflation. I think it would push us to abandon inflation. So it could be that just the theoretical advances do it. The second is there could be some observations that would be inconsistent with inflation. In a way, it's hard because we've done the microwave background. So if the microwave background showed the statistical properties of the fluctuations were not isotropic, the universe looked different over there than it did over there, that would be inconsistent with inflation. If it showed a pattern of fluctuations that were highly non-Gaussian, that would be inconsistent with inflation in the standard form.
But is that technically true? Again, I don't want to get into too many weeds, but isn't there, I've seen papers that describe an inverse problem where they basically go from sort of any form for the fluctuation spectrum and invert it to get a new potential for a multi-field inflationary scenario. Is that inverse problem well defined, and does it suggest that regardless of what you would have seen in the spectrum, you could have modeled it in an inflationary setup? It just wouldn't have been very simple, or elegant.
Yes.
Yeah.
Right, so this gets to the a lecture I heard Jim Peebles give many years ago of, science is art criticism.
Is what?
Right. Science is art criticism. Right. Theories often don't die. They get increasingly baroque. Right. You keep adding epicycles. Right. So an inflationary theory with a single field, a simple potential, ideally one that one can connect with deeper physics, fundamental physics, is very attractive. Yeah. An inflationary model where the potential looks like that and involves 5 different fields coupling together in odd ways starts to look like a pretty baroque model.
Right.
And often theories are often not ruled out by a particular observation, but driven into a baroque corner, and a new idea comes along that's a simpler explanation.
And so would you consider Paul's cyclic cosmology in the ballpark of that kind of simplicity and elegance that deserves attention, because it appears to be able to explain the microwave background data just as well as inflation and things of that sort, at least so he claims?
Yeah, I mean, I think at this point, we've got inflation becoming baroque in one corner with its initial conditions. I think you've got Paul and Anna's model with a very particular form of the potential needed to make it work, becoming baroque in a different corner. I think their explorations are really interesting because there could be some adjacent version of it. Like, they could be onto something. But, I don't think they've convinced the cosmological community yet that that's the simplest approach. But I think as the level of, is this something that I'm enthusiastic about their studying? Absolutely. Right. I think it's really vital to have these alternative models, and sometimes the alternative models become the standard model.
Right. Now, one of Paul's other criticisms that you briefly made reference to is that within inflation, it's pretty hard to have a single universe. As you noted, you have a rapid expansion in our observable universe. Ultimately, it stops. The inflaton field that drove that, it decays into the particles and make up matter in the world around us. But in other realms, it continues to expand and in some sense gives rise to universe upon universe upon universe because of that. Paul hates that idea. I myself view it as an interesting idea to have in your toolbox that may naturally emerge from a theory that may be confirmed in the manner that you described. If you get the gravitational wave beam mode in the CMB, it will add so much confidence in the inflationary model that I think we'd begin to take seriously all of its predictions, including the possibility of this multiverse. So I'm open to the idea, but I'm hesitant to give it a lot of weight because it's so hard to test, maybe even untestable, these other realms. Where do you come down on it?
Yeah, I mean, I share Paul's queasiness about the multiverse because it is untestable, but that doesn't mean it's wrong. And to me, the way forward, well, I think a big step forward is to go after the gravitational waves. That's like clearly going to help us if we see it. They'll clearly advance our understanding. So that's, the one of the paths we're on. On the theoretical side, I think we have these interesting open questions, right? And can we do we have to have an inflationary model that produces a multiverse? I don't know. The successes of inflation are all involved with the final 60 e-folds of inflation, the end moments. That's not when the multiverse was generated. The multiverse is generated early on towards the beginnings of inflation. So it could be, this gets back to our effective theory discussion, that it's the right theory at the low energies of only 10 to the 16 proton masses. Right. And, but when you get near the Planck scale, which is, 10,000, 100,000 times bigger, that the theory breaks down and it's a richer, more complex theory. I like the idea that the inflation theory we have is an effective theory. It's an effective theory valid only at low energies, which represent the end of inflation. And if we had the complete theory, it would avoid the multiverse problem. And I can say those words, but I don't know how to do the calculation.
Yeah, no, I don't think anybody does yet, unfortunately. But I think that's the most rational way of thinking about how inflation fits into the ultimate story, whatever it may be. As you say, it may be the end story, and we just need to fill in earlier chapters, or maybe it is just the way that we can talk about it today, and maybe string theory or something else will give us a whole new paradigm that agrees with inflation during those last 60 e-folds, but perhaps describes it in a different manner. In the remaining time, I'd love to spend a little bit talking about dark matter and dark energy, as they're so vital to the cosmological paradigm. We've been searching for dark matter forever, since it was first thought of in the 1930s by Fritz Zwicky and Vera Rubin later on. Is there anything in the failure to directly detect dark matter that would cause you to lose confidence that this is the right paradigm?
No, in fact, I think the astronomical observations have gotten better and better. And I mentioned that briefly in talking about the microwave background, that we see the imprint of the dark matter in the microwave background and can infer its abundance and its properties with very high precision now. So we know dark matter is there. We can test alternative theories of gravity that don't require dark matter by asking, do they fit the microwave background? And all the ones we have now don't. We can look at the growth of large-scale structure. That's all consistent with dark matter. But unfortunately, all this tells us about the dark matter is it's abundant, it's massive particles, and they don't interact much with photons. So there's a huge class of things that could satisfy that. What we've learned from the experiments is what the dark matter isn't. Yeah. We have put very serious constraints on the dark matter being the lightest supersymmetric particle, the stuff that we talked about 40 years ago, and was the best idea we had at the time. And the experimentalists have worked really hard and really narrowed the parameter space for that. but that leaves other interesting alternatives, particles like axions, or maybe something we haven't even thought of yet. It's relatively easy in a way to come up with a good dark matter candidate that by adding a wrinkle on the standard model of particle physics. And what we're waiting for is, I think, a hint, whether it comes from the Large Hadron Collider and it's at higher energies, from some experimental search for dark matter, maybe through its imprint, if it's a light particle that self-interacts on the shape and structure of galaxies or tidal streams. There are lots of people working on different ways of testing different dark matter ideas.
Yeah, and I share that perspective as well. I think we all have a certain kind of frustration that ideas that seem so incredibly natural. I mean,
Yeah.
I don't want to spend a lot of time reaching the end here, but this notion of the light as supersymmetric particle, which would be the stable particle that comes out of this natural extension of the standard model of particle physics, it almost automatically has an abundance of what you need to have left over from the Big Bang to be the dark matter. And so it's so convincing on paper, and it's so frustrating that the most natural idea seems not to have been borne out.
So, but if I remember our paper from 40 years ago, we had a more complex Higgs structure, which significantly lowered the interaction with ordinary matter. So I think our paper could be right, and it would have avoided the limits.
Yeah, I remember we had an additional neutral scalar field, I think, as part of the Higgs sector. Yeah, as well. So who knows? Who knows? Maybe we should have put it out. What about dark energy? So that's a curious one. We've now known since 1998 from the accelerated expansion of space that there is this energy that's pushing things outward. The simplest, again, from the mathematical standpoint, is a cosmological constant. Do you think it is constant, or do you think that the data like DAISY and so forth may be suggesting that it's not?
I think the data we have mostly suggests that it's constant. The DAISY data is a little bit off the constant model, but at the same distance, the Sloan data actually is has a value on the other side of that line. So even ignoring the theory, the two measurements are a bit off. And I would say they're likely a statistical fluctuation. So one of the pieces of progress in the past few years has been real improvements on our measurements of the expansion of the universe over time, using galaxy observations and the like. And they're all consistent with the cosmological constant being constant. We're about to get more improvements on those measurements with the Roman telescope that NASA will launch, with the Rubin experiment, named after Vera Rubin, one of the pioneers in the discovery of dark matter. So if we're lucky, it's not constant, because that would give us a hint about what it is.
Yeah.
And if it's constant, it's one number that we need to understand what sets that value. You know, we've known for a long time that theories can have vacuum energy, but it's a vacuum energy that's just remarkably small. We don't know why it should have that value, and that's a profound question, but one that I don't think we have a compelling answer for at the moment.
Now, that does bring us back momentarily to the multiverse, because people like Lenny Susskind and others have suggested that maybe if it is this ridiculously tiny number in natural units, like 10 to the minus 120 in Planck units, that maybe there are many realms, many universes, and that number has different values in each. And if there are enough of these realms, some of them will have this tiny value just because of the random variations in the properties of the universes. Does that at all grab you, or again, your resistance to multiverse is enough to say I don't buy that at all?
Well, both I'm resistant to multiverse, and if I take that theory seriously, you can ask, what value could the cosmological constant have and still be consistent with the observed universe? And the cosmological constant could be 1,000 times larger. And we could live in a universe in which the fluctuations we see in the microwave sky are 1,000 times brighter, and life would have existed. And it's hard to understand why the fluctuations in the microwave sky are as small as they are. So if I really took this multiverse seriously as a way of determining cosmological parameters.
Right.
And
but it still narrows you down more than you otherwise would, at least gives you an explanatory framework within the universe of values that's close to what we observe. And it's hard to do that in any other approach.
So philosophically, I find the anthropic principle, which is what we're talking about here, right? So the multiverse could be there, and we don't live with an anthropic principle.
Right.
We don't use it. Is basically an intellectual tautology. It's like you're saying, why are you wearing a white shirt today? And my answer is, if I wasn't wearing a white shirt, you wouldn't ask that question. That's true. And there's a universe where I could have all possible shirt colors.
Right, right.
The true answer is, I know for being on camera, a solid color shirt is better. I should have gone with a light blue shirt, but my light blue shirt was dirty.
Yes. So definitely have sympathy with that perspective. I also do at least find it interesting that it becomes a little less tautological if one realizes that there's a natural theory called inflation that seems to naturally give rise to this multiverse. And then if that happens to be true, then asking questions like, why are we in a realm with the properties close to the one, it becomes less tautological than it otherwise would be.
It becomes less tautological, but then if you take it seriously, the values we have don't necessarily
don't nail it down with that kind of precision. That I certainly agree.
Don't nail it down. You'd think you'd be in other parts of the parameter space if you're honest about it.
Well, it depends what measure you have on. So we do get into all sorts of subtle technical issues, but yes. So if you have time, I did want to ask one final question, if you can hang around for just another. All that we've been talking about here today is a dialogue between observations and mathematical theories. And it's an amazing thing that mathematics is this language that somehow is so readily applicable to understanding physical reality. And Eugene Wigner a while ago wrote a paper that I think from past conversations that we've had is both close to your heart and to mine, which is this issue of the unreasonable effectiveness of mathematics in the physical sciences. So after thinking about these issues for 40, 50 years, where do you come down? Why is math so incredibly good at describing reality?
So I have two answers to that, and I debate between them. And one is, math is almost the only language we have for creating a good description of what we see. We have to measure things, we have to express it in numbers. So if we can't use math to describe it, well, we don't have a good theory. That's kind of but I actually prefer a more profound one. There's something about the universe we live in that loves elegance. And I don't know why. The joking line is, I don't know who God is or what, but she loved mathematics.
And so do you think that when we perhaps one day do make contact with life beyond planet Earth, will they have developed effectively the same language called mathematics in their efforts to understand their reality?
So a lot of this comes down to, is math discovered or is math invented?
What do you think?
I think math is discovered.
I think it's invented.
A future conversation.
Yes, absolutely. So this has been a joy speaking with you, David. Thanks so much for joining us. And look, let's hope that the reference you made earlier, that maybe string theory or some other quantum theory of gravity will fill in our understanding of the early parts of the universe, allowing us to tell a more complete story. But it's remarkable the work that you and your colleagues have done to be able to tell the story of cosmology as we currently have it, which is an incredible achievement. So thanks so much for joining us, and I look forward to future conversations.
Real pleasure.
Thanks.